Good morning, students. In the previous class, we discussed about the product of vectors like scalar product and vector product of the vectors. And in vector product, we discussed some like properties of this vector product and applications of this vector product. And now let us see some basic numericals based on that. Product of that means vector product of the vectors, two vectors. So in this, for example, I am taking this a force F bar acts on a point like 2i cap minus 3j cap plus 4k cap newtons. So now acts on a point 2 comma minus 3 comma 1. All are in meters only, all those are points. Then we need to find the torque about this origin. Torque acting on this, the torque due to this force about this origin we need to find. So write that point. A force of 2i cap minus 3j cap plus 4k cap newtons acts on a particle placed at the point 2 comma minus 3 comma 1. Then find torque due to this force. Torque due to this force about origin and also find about 1 comma 2 comma minus 1. Like suppose this is point A, this is point B. That means about origin we need to find and about that point also we need to find. That means simply about origin means that is our general reference point. Sometimes they may give the reference point as a other point other than this origin. So then about that other points also we can find this torque here. So simply what we know is, if suppose I am taking our coordinate system like this is say x and y axis. And z axis will be there because three components are there. I am representing only plane here. In the plane just I am giving an idea. So then suppose this point is A here. Let us take this point as some A. And somewhere some other point will be there. These are in space only. You need to assume them as in space only, those points. And so then this is our origin here. So initially the force is acting here. The force is acting in some direction like this. Like F bar will be there along some direction. So now our first case, our reference vector is this one. Our position vector is this one here. So this is our R bar. In the second case, you can't take this as a reference vector here. You need to take from here. Between these two, we need to consider here. So that means with respect to this, we need to find the torque acting on this, right? That is the difference between those two problems there. And so first let us do our usual calculation. Our usual calculation means we can write this F bar is given here. So the torque we can write this as tau is equal to, our formula for this torque is tau bar is equal to R bar cross F bar. So R bar cross F bar. This we call tau, as I said in the last class. It's similar to that of our T, capital T. Just we write the top like that. And so now here you can substitute these vectors here. So now where this R bar is equal to, now for the first case our R bar is, you need to take this as a R bar. If point is no, then we know how to write this R bar vector. So you can write this as 2i cap minus 3j cap plus k cap. So this is our R bar. F bar is already given here. Therefore this tau bar is equal to this R bar cross F bar, and which we can write this as just we are writing the determinant here. And now the determinant is nothing but you can write this first our R bar here. Our first vector is R bar. So let us write the coefficients here. 2 comma minus 3 comma 1 and F bar 2 comma minus 3 comma 4. F bar coefficients. Now we can simplify this. We know already in the last class we discussed already about this, how to find this determinant of this. So then we need to find for I cap means we need to find these values. So minus 12 minus of minus plus you will get plus 3 minus j cap into, now we need to multiply these two first, 8 minus 2 and next plus k cap into, now we need to multiply these two, minus 6 and this is minus of minus plus 6 you will get. and therefore this torque will be equal to tau bar is equal to, this is minus 9 I cap and minus 6 j cap, right, and that k cap term will be 0 we are getting here. So this is the torque acting on this particle about this point A here or about point origin, and the unit will be like Newton meter we need to write, because that position vectors are also, as I said, these are also expressed in meters, like 2 meters comma minus 3 meters comma 1 meter. So that is a torque about that point. Now suppose if torque about is another point, if you want to find here. So for example, now we need to find torque about point B. So right, now we need to find the position vector of A with respect to B. So now let us see how to find that. So then I am taking this as some R1 I am taking here now. This position vector of B I am taking it as R2 for example. Now the position vector of this A with respect to B we need to write here. Now this is our reference. So our position vector of A with respect to B will be along this direction. This is position vector of A with respect to B. Right? And so now it is nothing but you can apply simply this triangle principle here, and out of this triangle then you can observe this, these two are taken in the same order, and so this will be the resultant. Or you may name this as, then it will be easy for you, you may name this as RA and RB. That means RA and RB are the position vectors of the points A and B. Now we are writing the position vector of A with respect to B. So from triangle we can write this as RA bar is equal to RAB bar plus RB bar, right? That means the sum of these two vectors must be equal to the resultant, this vector here. And so now just from that we can write this as RAB bar is equal to, or AB bar is equal to RA bar minus RB bar you can write. So that is our position vector here. Just even with respect to origin also, actually that is the meaning only. If you are writing with respect to origin, RA bar minus R0 bar we need to write. R0 bar means that is 0, 0, 1. So then you can substitute these values now. RAB bar is equal to, now RA means 2I cap minus 3J cap plus K cap minus RB bar. That RB bar is nothing but I cap plus 2J cap minus K cap. So right, so that is that vector. You can simplify this. RAB bar is equal to I cap minus 5J cap, and this is plus 2K cap. Now next again our torque calculation will be same. So simplify that. Like you need to write again this torque as torque about this point B is equal to RAB bar cross F bar. Same here, instead of this you need to substitute those values here and substitute them and simplify the equation there, right, in a similar way. So that means if they are giving, like sometimes they are giving the torque about this any other reference, so that is the procedure here. Then we need to find the position vector of the point on which that force is acting with respect to our given reference point. So here the B is a reference point. Our position vector is, you need to remember, our position vector is always away from the reference. So if the origin is our reference, then you should observe this, our position vector will be like this. If B is our reference, then it is away from this point B here towards the point whose position vector we are representing. And so like that we need to consider here. So then further simplification we can do. Just we need to find this determinant of those two vectors, this RAB bar and F bar, right? So it is the calculation of this torque. And next about angular momentum and then velocity. By giving angular velocity they may ask linear velocity. All those are applications or direct formula based only. So just by using that formula you need to write this R bar and F bar or R bar and V bar in case of angular momentum or P bar momentum. Then you need to find the cross product of those two vectors. Or in case of velocity you can write this as cross product of this velocity, angular velocity and position vector, right. So that means those problems you can solve based on that formula based only. And next we discussed some area applications, and that area applications also you can solve easily. But here sometimes that means those are also direct formula based only, and finally you need to find the cross product of those vectors. Either if suppose p bar and q bar are given as the two adjacent sides, then adjacent sides of this parallelogram, then area is nothing but like p bar mod of p bar cross q bar. If the r bar and s bar like diagonals are given, then half into mod of r bar cross s bar. And in case of triangle, if a bar and b bar are the two sides of the triangle, then area of the triangle is nothing but half into a bar cross b bar mod of. So then all those are formula based only. They will give some sides and then we need to find those values here. And now here I am giving some another problem here. So let us say this area calculation only. Suppose say these are the points A, B, C. This is say 1 comma 2 comma minus 1. This is 2 comma minus 1 comma 1, and this is, let us say this is minus 2 comma 3 comma 4. That means a triangle is given here. Those are the vertices of those triangle. Now we need to find the area of this triangle. So write that the three vertices of the triangle ABC are shown in figure. Three vertices of the triangle ABC are shown in figure. Then find area of the triangle. Then find area of the triangle. So if you know the sides, then we know how to write this area of the triangle. But here sides vectors are not given here. The vertices of those points are given, right? And so then you need to find the sides of the triangle from this vertices. Like our previously we discussed like RAB bar. RAB bar means we mentioned like RA bar minus RB bar, right? So similarly now here what I am taking as, I am taking this as a reference here. I am taking this as a reference vector. Now let us write this, I am writing like RBA bar. If you are taking this as a reference, you need to write this RBA bar. Then its direction will be along this direction. This is our reference, away from our reference, right? Previously we mentioned like AB bar, then B is our reference, then from B to A we mentioned in the previous problem. So similarly now A I am taking the reference, then its vector will be, the position of the B will be away from this. And so then here it is RBA bar. So which we can write this as RB bar minus RA bar. And let's suppose I am taking this as P bar here. I am taking this vector as P bar I am assuming, so that we can write that formula. And so now here this can be written as therefore this P bar is equal to RA bar, means you can substitute those values here like 2I cap minus J cap minus plus K cap. This is RB bar, and RA bar minus of I cap minus K cap. Right, and therefore it is P bar is equal to, so P bar is nothing but what we are finding is AB bar, one side we are finding here. I am assuming that as a P bar, and so then you can write this as I cap minus 3 J cap, and this is plus 2 K cap. So right, so that is one side here. You can name any value, any letter here. I am taking it as a P bar, or you can write this as AB bar. So this is one vector, one side, and similarly you can find any other side you can find here. So other side, for example, again I am taking this as AC bar. That means position vector of C with respect to A I am writing here. So that means now I can write this as RCA bar is equal to RC bar minus RA bar, right? So then again same process. RCA bar is equal to, RCA is nothing but you can write this as directly substitute those values here. So if you are substituting this, then this value is minus 2 I cap plus 3 J cap plus 4 K cap. This is RC bar, minus RA bar is nothing but I cap plus 2 J cap minus K cap, right? and we can simplify that. You will get this, let's suppose I am taking this vector as some q bar for example. So let us take this as some q bar here. Therefore, this q bar is equal to minus 3 I cap plus j cap plus 5 k cap. So now this is our q bar vector here. Now we know the two sides of this triangle here. So we got now the two sides of the triangle. So any two sides we can find like that, right? And so then by using this now we can find the area. So therefore this area of the triangle we can write this as, so area of triangle is equal to half of mod of p bar cross q bar, right? If p bar and q bar are the two adjacent sides of this triangle, then our area of the triangle is nothing but half of mod of p bar cross q bar. So then you can find this p bar cross q bar value and then we can find the modulus. You can do the remaining calculation here. So p bar cross q bar is equal to, so this is I cap, j cap and k cap. So p bar means it is 1, minus 3 and 2, and this is minus 3, 1 and 5. So therefore find this value here, I cap, this is our p bar cross q bar value. So this is I cap into, I am directly writing this, is our minus 15, minus 2, minus j cap into these vectors 5 plus 6 plus k cap into 1 minus 9. And so now further you can write this as p bar cross q bar is equal to, so now this vector is nothing but minus 17 I cap and this is minus 11 j cap minus 8 k cap. So find the magnitude of this and find the area of this, half of this triangle here. That means area of this triangle, half of that magnitude. Therefore this area is equal to half into mod of this value we need to write here. That means under root of 17 square plus 11 square plus 8 square. That means if units are not given, then just we write the square units, or otherwise if meters if it is mentioned, then we can write this, you can write this units there. Just I am writing it as a square units. If meters if it is, then square meter square you need to write. If it is centimeters, then we can write it as centimeter square, right? So simplify that value. And so that is, if vertices are given, then that is a way of finding this. So I am not calculating any further applications based on this. The remaining will be direct formula based only. They will give the two sides of either parallelogram or triangle. Then we can directly find the cross product of those two vectors, and from which you can find the area, right? So it is just area for area. I am giving only this example. And next, the another applications, or sometimes there may be questions for finding the torque and angular momentum related to our projectile motion. So let us see one such application here. So write that problem. So general problem I am saying now. An object is projected with initial velocity u, at an angle theta with horizontal. If m is the mass of the particle, find torque and angular momentum of the projectile, about point of projection. So in that first question, let us write it as A, at any instant of time. And the second one is when it is at highest point. And the third one is just before reaching the ground. just before reaching the ground. So if at time first one if you calculate, the remaining two you can just substitute those t values, but in general they may ask about highest point and point of, that means about this landing point frequently, so that I am giving those expressions also now. So then this is our first, if you know how to calculate the first as a function of time, the remaining you can solve it easily. So then here to calculate this torque, for example, if you consider our torque definition is nothing but r bar cross f bar, right? So we need the position vector and force vector. Can you say what is the force acting on this projectile? So first we are solving this. So can you say what is the position vector of the projectile and what is the force acting on this projectile here? What is the force acting on the projectile? The only force acting on the projectile is gravity. If a body is moving under the action of gravity, then we call only under the action of gravity, then we call it as a projectile, right? So that means the only force must be the gravitational force here. And so then here, this is our torque formula here. So just mention that we know torque is equal to torque tau is equal to tau bar is equal to r bar plus f bar. So now where this f bar is nothing but, let us take our usual coordinate system, like horizontal I am taking as x axis and vertical I am taking as y axis, our usual coordinate system, so that I can write this as minus mg j cap, right? So we know gravitational force will be vertically downward direction. And next we need to write r bar value at any instant of time. So for example, I am taking this somewhere at any instant of time, the particle is here, having some velocity along this direction here, right? Then its position vector means, so its position vector in projectile motion, position vector at any time you can write this as simply xi cap plus yj cap you can write. So simply this is the way of writing the position vector at any instant of time, where x is horizontal displacement of this projectile and y is the vertical displacement of this projectile. So that is the meaning of that simple x and y. And so now you know how to write this x and y values, right? So then how to write x and y values means horizontal displacement and vertical displacement. So horizontal displacement you can write as horizontal component of velocity into time, I cap. Got it? We know x value, u cos theta into t. And how to write vertical displacement? S is equal to ut plus half a d square, along y axis we need to write. So then you can write this as u sin theta into t minus half gt square into j cap, right? So that is our vertical component of this displacement. So now this is our position vector. So now we got the position vector and as well as we got the force vector. So now we need to do the torque equation here. We need to write this torque calculation. So now let us write this torque calculation here. So therefore this torque tau is equal to, so then our r bar cross f bar, so which we can write this as I cap. I am writing this I cap coefficients for this r, u cos theta into t. J cap coefficient is u sin theta into t minus of gt square and into k cap, right? K cap is not there. When that k component is not there, we need to write just 0. Next write is f bar value. So then f bar coefficient is I cap coefficient is 0. Then j cap coefficient is minus mg. And a k cap coefficient is 0. So right. So now those are the coefficients values here. Now we need to simplify this. So now we need to simplify this vector here. Therefore this tau bar is equal to I cap into, if I write the product of this I cap. So say this, we need to neglect this 0 and this term is also 0. So that there is no I cap term here, 0 minus j cap into. So now j cap means again we need to neglect this term, the product of these two 0 and the product of these two 0. So j cap term is also not there, right? plus k cap into. So plus k cap into. So now observe this. K cap means now this term we need to neglect here. We need to multiply these two terms and then these two terms. So then what we can write is minus mg into u cos theta into t, and minus 0 actually we need to write here, and therefore this torque at any instant we can write this as minus mg into u cos theta into t k cap, right. So this is the value of this torque acting on this projectile at any instant of time. So if I ask simply the magnitude of this torque, the magnitude of this torque we can write as, so this modulus of this tau bar I can write as simply mg into u cos theta into t. So this is an expression for this magnitude of the torque at any instant of time, right. So that simply I can explain it in a simple way. Instead of doing all this calculation, we can solve it in a simple way. So just to see this, so then for this at any instant of time, without doing all this cross product and all these things, you can write it in a simple way. So at any instant of time, suppose the particle is here, right, then this mg is acting like this. We know force is vertically downward direction. So then we can write this as force into perpendicular distance. That is nothing but what we defined here, right. So we are finding this, we are finding the torque about this point here, about this point of projection we are finding. So let us go back to the definition of the torque. So in the basic, before writing this cross product, the torque we defined as force into perpendicular distance. Perpendicular distance from the line of action of force to a reference point or the axis of rotation. So then here this is the line along this vertical line. So this is our reference point. So this distance is nothing but we call the perpendicular distance here. The distance between the shortest distance between line of action of force and the reference point. And you know this x value you can write as u cos theta, right. So therefore this magnitude of the torque, what we can define it is mg into x, and that mg into x is nothing but u cos theta into t you can write here. So that is nothing but what we are getting there, right. So just to learn that one also, and this is the general procedure what we are finding here, got it. That is the torque about point of projection at any instant of time. So then that is the force here, and next torque here, and next let us calculate about this angular momentum. Now here itself we can find the torque about the different points you can calculate here. So let us find the torque about the different points, then after that we will discuss about the angular momentum, right. So now I am calculating the torque about the different points here. So I will drop here. So now when the torque at the highest point, when the object is at highest point, so when the object is at the highest point A, so just if you are using this formula, you can substitute this time taken as time of ascent, right. So then time taken we can write this as tau bar or mod of this tau bar is equal to mgu cos theta into Ta. The time of ascent we need to substitute here. So just that T is equal to Ta, time of ascent, which we can write this as u sin theta by g, because you know total time of flight will be 2u sin theta by g, only half we need to consider here. Therefore this mod of this torque, or simply tau, is equal to mg into u cos theta into u sin theta by g, right. And therefore this value what we can write it is mg into u square sin 2 theta by 2g we can write. That means I am dividing and multiplying with this. So this is the torque magnitude when it is at the highest point, about this point of projection. Now this value also you can write easily if you are using this concept for at the highest point. If you are using this concept here, just let us identify the force and the position of this particle here. Now the particle is here, right? Now the particle is here, so this now the force is acting mg vertically downwards like this. Now when the mg is acting vertically downwards here, the perpendicular distance from the line of action of force means this distance. So which is nothing but r by 2, half of the range. So then torque you can directly write as mg into half of the range. Now we can observe that mg into r by 2. So then you can observe that this is nothing but our r by 2 here. U square sine 2 theta by 2g we are writing. So u square sine 2 theta by g is nothing but our r. So then mg into r by 2. So like that also you can directly write here mg into this distance r by 2 you can write, and where r is given by this expression. Like that also you can write, or just we are substituting the t value here. And now similarly basing on this you can write torque when it is at the highest point, just before landing. So just let us write the torque when it is just before landing. Torque on projectile just before landing. So that means just before landing means at the point B here, just before reaching this surface. Then what we can write is this torque tau is equal to mg into u cos theta into t we need to write. So simply that t is equal to capital T, which is nothing but 2u sin theta by g. If you are using that formula, if you are using the formula mg u cos theta into t, the t means we need to substitute this capital T value here. And so which is nothing but this tau is equal to mgu cos theta into this t value is nothing but 2u sin theta by g we need to write. And therefore this tau is equal to mg into u square sin 2 theta by g. I think from this it is clear to you. You can also write it in a shortcut way, like when particle is here, mg is acting here. When particle is at the point B, then the perpendicular distance is nothing but, shortest distance is nothing but our range r. So then mg into r, that is nothing but what we are getting here. That means this value you can write this as mg into r. So that is the range. Got it? So that means either you can use this formula, or that means especially when it is at the highest point or this point, you can use this shortcut way here, mg into this distance you can write. And when it is at any instant of time, if they are asking, then you can use our general formula mg u cos theta into that horizontal, that means mg into horizontal displacement. At any instant of time we need to write if they are asking at any instant of time. So that is about the torque calculation in case of this projectile motion, right? And so now let us similarly discuss about the angular momentum calculation here. So now let us see this angular momentum calculations. So what is the definition of this angular momentum, or what is the formula for this angular momentum? R bar cross P bar you can write, or R bar M into R bar cross V bar you can write, right? So here also at any instant, first let us calculate here so that you will get the clarity about that. Again let us take the particle is somewhere here, so that these are same x and y, right? And now let us say this angular momentum calculation here. So angular momentum L bar is equal to R bar cross P bar, or you can also write this as R bar M of R bar cross V bar, right? So previously we write just R bar cross F bar we mentioned there. Now we need to write R bar cross V bar we need to write here. Just that is only the difference there, right? Now again, now at any instant of time if you want to calculate, first we need to find these two values at any instant of time. Therefore velocity at any instant of time. So velocity at any instant of time means just our procedure is Vx I cap plus Vy j cap we need to write, components we need to write. And therefore this velocity at any instant, x component of velocity is u cos theta I cap, and you know it remains constant. And y component, to find the y component of velocity we need to apply v is equal to u plus at along the y axis, right. So plus this is u sin theta minus gt j cap. So that is our velocity at any instant of time. And next position vector means as it is similar to that of our previous one. So this is position vector. R bar is equal to, directly I am writing here, u cos theta into t I cap plus u sin theta minus half gt, that y component of displacement we need to write u sin theta into t minus half gt square j cap. So now this is our position vector now. And just our angular momentum means we need to write our cross product formula here now. Therefore this angular momentum L bar is equal to R bar cross V bar into M. M you may write here first or last you can write. Therefore this, and so first let us calculate this R bar cross. So first I am calculating like R bar cross V bar value, and after getting that you can multiply with that M. So now our calculation will be like this. So I cap into, now a coefficient of this I cap you need to write R u cos theta into t, and for velocity, or let us write all the values, then after that we can substitute this. This is for this u sin theta into t minus of gt square, and this k component k cap 0. And now for this velocity if I write, x component is I coefficient is u cos theta, and this term will be u sin theta minus gt, and this is 0. Just you need to find the cross product of this, and if numericals are given, then calculation will be easy for you. Then otherwise it will appear some lengthy calculation here, nothing to worry. Then generally numericals will be given, so you can calculate that easily. So then here what we can write is, so let us simplify this, I cap into, so we need to neglect this, so we need to multiply these two terms and these two terms, so that will be 0, minus j cap into, so again we need to neglect this term and this term, so that is also 0, j cap coefficients. So now this k cap coefficients we need to write, the product of these two. So that is I am multiplying that u square sin theta into cos theta into t minus g into u cos theta into t square, and minus these two values you need to write here. So that minus of, I am again writing those values directly here, minus of u square sin theta into cos theta into t, and minus of minus plus you will get half gt square into u cos theta, right. And now you can simplify it easily. This first term and this term and this term will be cancelled. So therefore this R bar cross V bar vector value is minus g square g into u cos theta into t square by 2 k cap. So just we need to simplify these two terms here, then minus 1 by 2 you will get. So that means gu cos theta into t square you will get, right. So that is now our R bar cross V bar. Therefore our angular momentum is m of R bar cross V bar we need to write. So which is nothing but you can write this as L bar is equal to minus mg into u cos theta into t square by 2 k cap in vector form. And if you want to write that in magnitude, you can just eliminate that modulus of that, then minus k cap you can eliminate there. So this is in vector form it will be like this. So whereas its magnitude will be mg u cos theta into t square by 2. So that is a vector form component there. That means magnitude and vector form here. The magnitude of this angular momentum. So like that you can calculate now. And for this also, this our r bar is nothing but you can define that as a perpendicular distance you can define here. By finding the perpendicular distance, you can calculate that value. So instead of finding this, we can resolve this velocity into components and you can find that. So at any general means you can remember this equation here. So then by at any general value means you can remember this. And actually in Newton's laws, if you know already the Newton's law statement, from that you can write this expression. If you know the torque expression, you can write the angular momentum expression easily. If you know, then you can understand that, otherwise leave this what I am going to say, or otherwise you may follow this. That means we know this torque force is equal to dp by dt, rate of change of momentum, right? Rate of change of momentum. And now the torque, similarly the torque you can write as rate of change of angular momentum, you can write here. Rate of change of angular momentum. So then just to find this angular momentum, if you know the torque equation, just you need to integrate this. So we got already the torque equation as mg into u cos theta into t. So just we need to integrate that mg into u cos theta. Mg into u cos theta into t into dt. So here just this integration, then that gives the total angular momentum here from 0 to t. That 0 to t is nothing but t square by 2 you will get. That means this is the Newton's law in linear motion. Similarly this is the Newton's second law in angular motion, that means rotatory motion. We will discuss it later. If you know this, you can also calculate like this, or otherwise this will be the general procedure. If you don't know this, don't bother about this. We will get these values, we will get this calculation in this say rotational mechanics. We will discuss about the Newton's second law in rotational mechanics. Don't bother about this. You can follow that procedure there, right? So then that is a calculation of this. Just if numericals are given, then this calculation part also will be easy for you. So then next let us go to the angular momentum at the highest point and at the point B. This is at any instant of time, that is a calculation now. So let us write when the angular momentum when it is at highest point. So highest point means in this expression again you can substitute that t value there to get the angular momentum at the highest point. So that is our expression here. So I can write this so angular momentum at any instant, the magnitude of angular momentum. So then yes, this value will be L is equal to mgu cos theta into t square by 2 you will get, right? That is angular momentum at any instant. Now we need to write angular momentum at the highest point. Angular momentum when projectile is at A, that means highest point, that is. Right? So when this at this highest point means, then just we need to substitute that value as the t value as time of ascent we need to substitute here. So directly I am substituting that. So mg into u cos theta by 2 into what we are going to substitute is time of ascent. Time of ascent is nothing but u sin theta by g whole square, right? Because t square is there. Just what we are substituting is t is equal to time of ascent, which is nothing but u sin theta by g. Just we are doing that substitution here. And so now let us simplify this equation here, so that you will get this expression as L is equal to mg into u cube. Here already u is there, and then here u square you will get u square, and 1 g will be cancelled actually. So I am writing this final answer here, m u cube. Here actually g will be there, and here g square you will get. So one that the g in the numerator will be cancelled, the denominator will get 2g. And so I can write this as sin square theta into cos theta by 2g you can write. And if you want to do any conversions like 1 of the sin theta, you may convert it into sin 2 theta formula, and you can do that. That depends on the options. How the options are there, according to that you need to convert this, right? So that is the general equation here to find this angular momentum at that when it is at highest point. And for this, when it is at highest point especially, you can also calculate that angular momentum directly. That means without using this formula here. So then let us see how to calculate that. So that means angular momentum when it is at highest point, you can write this as, suppose I am taking that when the particle is at this highest point here, then angular momentum what we are writing is, you can write this as the linear momentum, perpendicular component of momentum into this distance you can write here, perpendicular distance. That means you can resolve this components of momentum into components. Like for example here, what we discussed is when the particle is here, the momentum of particle is somewhere like this. Then you can resolve this into momentum components here. If this is suppose say theta, then this is p cos theta you can write, and a p sin theta you can write. And now this about this origin if you want to calculate here, then you can write the angular momentum due to these components you can write here. Like for example, I will explain with this clear diagram here. By resolving these components also you can write here. Like suppose say the particle is traveling along this direction, along this line it is traveling, so its momentum is along this direction for example, right? When it is at this instant, when the particle is at this instant, suppose if we need to find the angular momentum, then one way is for this, from this momentum direction you can find the perpendicular distance. So that you can write this angular momentum as p into that r perpendicular you can write, where r perpendicular means this value. That is one way. The another way is you can resolve this momentum into components. For example, here I am taking that this angle as some theta if I am considering here, then this will be p cos theta and this will be p sin theta. Then due to this p sin theta there won't be any angular momentum, because that p sin theta is passing through this reference point. Whenever momentum is passing through that reference point, there won't be any angular momentum. And so then due to this there is no any angular momentum here. Now due to this that angular momentum will be there. So then for this p sin theta into this will be the distance here, perpendicular distance. Now directly suppose if it is b, then p sin theta, p cos theta into b you will get, that will be the angular momentum. So I can write this angular momentum as p cos theta into b. And even if you calculate by using this p into r perpendicular, that also will get the same expression. Let us see this. If this angle is theta, then here this angle will be theta, right? In this triangle, if this angle is theta, then this angle will be theta, because this will be 90 minus theta you will get, and so that this angle will be theta. So in this right angle triangle, this is the right angle here. So in this right angle triangle, this is the adjacent side and this is a hypotenuse. So according to this definition, p into the r perpendicular is nothing but I can write this as d cos theta. So both are same. Either you can find perpendicular distance from the direction of the momentum, or you can resolve the momentum and components you can write here. Now similarly, when the object is at highest point, so the momentum direction will be along this direction, right? When the object is at highest point. So then, and its momentum is nothing but mu cos theta when it is at the highest point. Now this perpendicular distance is nothing but this value we can write here, the perpendicular distance, because this is the line of action of line of this momentum here. So this is the perpendicular distance. Similar to this is our p cos theta, this is a perpendicular distance for this p cos theta component we are taking here. So like that also we can calculate. So that in second method, what we can write is angular momentum is equal to mu cos theta into perpendicular distance h you can write. Observe this. So for this, draw this diagram here. I will draw the diagram here because according to that we are calculating this. So that means for this what we are taking is mu cos theta is along this direction, momentum, this is nothing but our momentum. Now this is the perpendicular distance here. So this is nothing but our r perpendicular. So right, so that mu cos theta into r perpendicular we are writing here. So we can write this as mu cos theta into this perpendicular distance is nothing but maximum height u square sin square theta by 2g, right? And therefore if I simplify this, mu cube into sin square theta into cos theta by 2g. Now we can observe that either by doing that cross product method, this is nothing but by cross product method here. By cross product method we are getting the same answer as that of this method also. That means either you can solve particularly for this highest point and for point of projection, such a facility is there here. You can calculate easily there. If you want to calculate at any other position by using this method, you can calculate, but again it will be lengthy as that of this difference, that means as that of this determinant method here, cross product method. Because if you want to find velocity at this instant, angular momentum at this instant by using this method, if you want to find, then you need to find the velocity at that instant and angle made by the velocity with the horizontal you need to find. That means direction of momentum you need to find. Again it's a lengthy process. So for that at any instant of time if they are asking, you can follow this. If the highest point they are asking, you can follow either like that or you can also simply write like this. Direction of momentum is along horizontal, then h will be the perpendicular distance here. So that this p mu cos theta into this h you can write. Now similarly, when it is just before landing the ground. So suppose if I am writing about that point here. So now let us see this. So angular momentum just before landing. Angular momentum just before landing. So simply first I am calculating by this method. So L is equal to mgu cos theta by 2 into t square. The t is nothing but we need to substitute it as time of flight. Time taken to reach this point is nothing but our time of flight. So it is nothing but 2u sin theta by g you can substitute here, right? And so that is whole square we need to write. 2u sin theta by g whole square. And therefore on simplifying this I can write this as angular momentum is equal to at that point m u cube or 2m u cube sin square theta into cos theta by g, right? So that means additionally here this 2 square 4 will be there, and so then 4 and 2 will be there in numerator, and remaining calculation is same as that of our previous. So that means that is the angular momentum when it is at before landing here. That means you can observe that it will be like 4 times that of the highest point. Angular momentum is nothing but t square. It is directly proportional to t square here. Time is doubled here, so that the angular momentum will increase by 4 times you can say when your particle is moving from highest point to this point. Now this you can solve by that method also, right? And so if you are calculating by that method, so let us see this now. If you are calculating by this method, for example, so let us identify the angular momentum when it is at just before landing here, direction of this angular momentum. So the second method we are using for this calculation here. So that means when it is landing here, we know that 2 components of velocities will be there. Horizontal components will be there and vertical component will be there. And so then one vertical component what we can write is mu sin theta. It will be along this direction, right? And the other component, horizontal component, will be there like this, mu cos theta, because we know when the particle is reaching this ground, it reaches this with the same speed, right? Or same component will be there, same magnitude of components of velocities will be there. So initially it is u sin theta will be upwards and now it will be downwards. That is only the difference there. Horizontal component remains same. And now clearly you can say that there is an angular momentum of this object due to this mu cos theta component, because mu cos theta component is passing through this point. So the perpendicular distance will be 0, so that there is no angular momentum due to this component. So no need of considering this component here. Then there will be angular momentum due to this mu sin theta. And so for this mu sin theta, then this distance is nothing but our perpendicular distance here, r perpendicular. And you know this, now r perpendicular is nothing but our range. So when it is at highest point, our r perpendicular is nothing but our maximum height we are getting here. And when it is at just before landing, then r perpendicular means we are getting like this value, range. And therefore this angular momentum we can write this as momentum mu sin theta into perpendicular distance, range. And therefore this is nothing but, that means actually this is nothing but momentum into, or component of momentum into perpendicular distance we need to write. Perpendicular component into distance we are writing here. That is actual meaning, because we are resolving momentum into components first. And so that this is nothing but mu sin theta into, this range is nothing but u square sin 2 theta by g. Right? So that is our range. And so therefore I can write this as L is equal to mu cube sin theta into sin 2 theta by g. And these two are same only, right? Just if you are writing that sin 2 theta, if you are expanding that, then that is nothing but you will get this expression here, 2 mu cube into sin square theta into cos theta by g you will get. So this is our angular momentum just before landing this, right? So that is the angular momentum calculation in case of projectile. So then those are some applications based on this projectile here, right? And then in like we derived an expression for component of one vector along the other vector in dot product. So based on this also one important model will be there. So let us see that model now. So now that problem is, note down that problem. If a bar is equal to 2i cap minus j cap plus k cap, and a b bar is equal to I cap plus 2j cap and minus k cap, then find component of a bar perpendicular to the b bar. Component of a bar perpendicular to the b bar. So then actually in the products of vector, like dot product, we discussed one of the application, like the component of one vector along the other vector we discussed it there, right? Now here they are asking that component of one vector perpendicular to that vector they are asking here. And so now for this what we can use is, we can use our component of one vector along the other vector. Suppose if two vectors are like this, we know component of a bar along b bar, we already discussed this. Component of a bar along b bar is given by this vector, like a bar dot b bar into b bar by b square. So then I am just substituting those values here, then dot product 2 minus 2 plus minus 1 you will get, and this is b bar is I cap plus 2j cap minus k cap, by this b square means the mod of this value, square of that, so 6 you will get. So that that parallel component, the component of a bar along b bar means that I am naming it as a parallel component, parallel to b bar. So that component we are getting it as minus 1 by 6 into I cap plus 2j cap minus k cap. Now we are going to calculate the perpendicular component. So for that what I am assuming is that AT, that means a perpendicular, this is a perpendicular bar with the component of a bar perpendicular to that b bar I am assuming here. So actually if you know the two perpendicular components, we can write the vector. Like if it is along x-axis, the vector component values for example 5, and along y-axis for example 4. then you can write that vector as 4 I cap plus 5 I cap plus 4 j cap you can write. If these are the components so like this, if 5 is acting, 5 Newton's force is acting along this and 4 Newton's force is acting along this y axis, right? If you know the two perpendicular components which are said to be rectangular components, then you can write this vector as 5 I cap plus 4 j cap you can write. That means now it is a component, these two are the perpendicular components here, rectangular components. So similarly now these two are such a components here. So then we can express that vector like this, parallel component plus perpendicular component. And so from this I can write this perpendicular component is equal to A bar minus of this parallel component we can write. So then A bar, this is what we are giving here, that is 2I cap minus j cap plus k cap. Then minus parallel component we need to write. Here already negative sign is there, so minus of minus plus you will get, right? And so then plus 1 by 6 into I cap plus 2j cap minus k cap. And on simplifying we are getting this. So this is the perpendicular component, that means this is the component of A bar perpendicular to the B bar. So easily we can find the perpendicular components like this. And if you want to verify this, whether this component is perpendicular or not, we know this dot product. So that means if these two are perpendicular or not, means if the dot product of those two vectors is 0, we can conclude that those two are perpendicular. So I am taking this now dot product of this perpendicular component and the B bar. So that means our A parallel component is along this direction. This is our A parallel component and perpendicular component will be along this direction. Right? Now these two are perpendicular, so their dot product should be equal to 0. Just I am verifying this. This is not required for us. Just we are verifying whether they are perpendicular or not. And so if we find the dot product of those two vectors, this vector and this vector, we can observe this 13 and minus 8 and plus minus 5 you will get. So it is nothing but 0. That means they are perpendicular to each other, we can conclude that. So that is a way of finding the perpendicular components here in case of these vectors, right? So those are some applications. Based on the remaining simple problems will be there, you can solve them. You can practice those problems. I will share a worksheet based on this. And next, after this triple product of vectors is also there. So that I will explain in our next class, right? Thank you.